Right, today we're going to talk about graphing polynomials. We're going to take a look at Desmos as well when we graph these. A few key ideas to be aware of, to know, is that we talk about the degree of a polynomial as being the highest exponent within a polynomial. Something to recognize within polynomials is even the lowest degree is always 0. What we have here is there's an exponent of 1 on this x right here that we don't see, and obviously we're not seeing because there's a coefficient of 0 to this x that also has an exponent of 0, and of course anything to the 0 is 1. So all of this here we don't actually see it because it's unnecessary, okay, including that 1. So the degree of a polynomial is the highest exponent for that polynomial. And the second thing to note there is the coefficient to that variable, right? So the variable that has the highest degree, the coefficient to that variable is called the leading coefficient, right? So this 4 here is the leading coefficient to the entire polynomial. Okay, so let's take a look at polynomials written in standard form. Okay, so first of all, we always write a polynomial with the highest exponent at the beginning, right? So this one here, f of x is equal to 8x to the 5th minus 4x to the 3rd plus 2x squared minus x minus 3, right, is in standard form because it's written from highest to lowest exponents. The degree is the highest exponent, so it's got a degree of 5. And the leading coefficient is the coefficient that goes with the variable that has that degree. So the leading coefficient is an 8. Okay. The second one here, smaller polynomials, 4x squared minus 1. The leading coefficient of that is a 4, and the degree is a 2, right? Because it comes from the exponent. Right? Take a look at this one here. This one here is not written in standard form. So let's rewrite this one in standard form first of all. Okay, so rewrite in standard form. We've got f of x or y, whichever way you want to write it, is equal to, we choose the highest one first. So this 8 here, this x to the 8 comes first. So we got negative 4 x to the 8. And then we've got, the next one is this 3x to the 4, so plus 3x to the 4. And then we've got our 6x cubed plus 6x cubed, and then plus 2x. Right. So now we can see that our degree is the 8, and the leading coefficient is a negative 4, even though that's not what we're seeing when it's not written in standard form. So writing in standard form has to be written from highest to lowest. Okay, let's apply this to a few examples. Right. There's actually an error in this here. We're going to find that error real quick. But I remember there being an error here that hasn't been fixed. So what we can do with polynomials is we can always plug in a value for the variable r, okay, and use that to solve for that variable, right? So in this case here, if we want the value of the function f at r equals 6, so when r equals 6, then we just plug in 6 everywhere we see r. So this here gives us 36 times 3 minus 3 times 6 is 18 plus 1, and hopefully you notice that is not equal to 37. So 36 times 3 is 108 minus 18 plus 1 is 91. Right? So somebody did the order of operations incorrect in this one here. But notice that first you've got to square the 6 before you multiply times 3. Okay, second example here, we're going to plug in 3 for x, right? So once again, we're just going to plug in 3 everywhere we see x. So we get 2 plus 4 times 3 minus negative 3 cubed. Now once again, we've got to cube this first, right? So we get our 27, right? So we get negative 27, and then we can do our addition and subtraction. So this is, of course, minus a negative becomes a positive. So 2 plus 12 plus 27 is equal to 41. Okay. Applying this to a few examples now where we're not guided with it. So all we're going to do here is we're going to plug in 2 every time we see x. So every time we see x, we've got 3 times, now we see an x, so we put in 2 squared minus 3, and we've got another x there, so plug in a 2, and then plus 1. Okay, so 2 squared is 4, so that's 3 times 4, minus 3 times 2 is 6, plus 1, and that's equal to 12, minus 6, plus 1, which is equal to 7. All right. Same idea with negative numbers, just watch out for the negative, right? So with this one here, we've got negative 1 cubed, that's plugging in for the first x, plus 3 times negative 1 squared plus 4. Okay, now watch out for those negatives, because a negative 1 is easier because you don't have to really worry about the value, the number itself increasing, but the sign changes. Okay, so if it's an odd exponent, the sign stays as a negative. If it's an even exponent, it changes to a positive. So with this one here, negative 1 times negative 1 times negative 1 is still equal to negative 1. Okay? Because negative 1 times negative 1 is positive 1, and then positive times negative becomes back negative again. All right. So we're going to add negative 1 times negative 1 is 1, so that gives us 3 times 1 plus 4, and that's negative 1 plus 3 plus 4. It's going to be a 6, I hope. Okay. All right, so that's the first part of this, just plugging in values for the variables and solving. The next part is actually graphing these. So we're going to pull up Desmos and we're going to take a look at graphing some things, right? But there's a few things. I'm not going to show it right here. I'm going to pull it up on Desmos so you can actually see it. But these graphs, different graphs look differently, right? So we're going to look at graphs that have a degree of 0, degree of 1, 2, 3, and 4, and 5, right? So let's pull up Desmos and take a look at that, okay? So a graph that has a degree of 0, right? So a degree of 0 is a graph that's y equals, say 1, right? So typically what we're saying is this is 1x to the power of 0, right? I'm putting in the 0 there so you can see it, okay? So that's a degree of 0. So you can see it's a straight line. There's nothing happening to it. It's just straight line. It's a constant, right? Essentially, it's what it is. All right, so let's look at another one. So we got y equals, in this case, we're going to go, okay, degree of 1, okay? So we're going to say 1x to the power of 1, right? And we're going to say plus x to the power of 0. Okay. Again, all we're doing is we're just extending onto it, right? Keeping it simple. You can see that this is a linear equation here. Okay. Obviously, if you were to change the coefficient, it's just going to change. You know, see the coefficient here. If we change it to 2, it's just going to change how steep it is. Okay, that's the slope. If you remember from 8th grade, it's the slope. Okay. When we bring it up to the second degree, okay, so x squared, okay, what you can see now is we've got a curve going on. Okay. Now this curve can go two different ways because, well, what if x is negative? Right? Negative versus positive. And that makes sense because if your x value is negative and you're squaring it, it's still going to go up. If your x value is positive and you're squaring, it's still going to go up. But if you add a negative in the beginning of it, then you're looking down and down. Okay. So a second degree, that's what that looks like. There's not much shift, but there's a little bit of shift when you have a variable of degree 1 along with it. So what you can see here is it's just shifting it left to right. Okay, I'll just erase that so you can see it. So there's your x, there's with your x, there's without your x. Right? If we added, say, 4x, it's shifting it down and to the left. Okay, so it's moving it. Right. The third degree, y equals the third degree, you can see, goes for negative values of x, y is negative. For positive values of x, y is positive, right? And that makes sense again when we talk about the negative 1 times negative 1 times negative 1 is going to be negative, right? But if positive 1, doesn't matter how many times you multiply it, it's going to be positive. Things start to get a little bit more interesting now when we add in higher degrees, x to the 4. Okay, so I'm going to start by kind of cleaning up a little bit here so you can see what's going on here. For x to the 4, you can see that there's actually a little jump starting. There's a flat line here. We can't really see it very carefully, very easily, but it increases slower at the beginning, right? It's a little bit flatter. Okay, and x to the 5th looks the same kind of idea again. Right? Flatter, but again, it's odd, so you've got negatives going along with it. And I think the last one, did we have a 6? No, we were just looking up to 5. But when you go 6, 7, it's just an extension of all of those. Okay, and of course you can add to these. I'm going to add to these and say, well, that's x to the 4, and you can see what's going on here. You're getting a little jump in it, right? Plus x to the 3 plus x to the 2 and plus x. Right? So you can see, like, polynomials start giving us curves that have a little bit more character to them. Okay. So Desmos is going to be a useful tool to be able to analyze these because it can give you things like your x-intercept, your y-intercept, and so on. All right. So we'll use that more. Okay. But you can use that to fill that out. So if we're to look at a few examples right here, we take this example here, and watch out, if you're copying pasting into Desmos, note what happens. You lose your exponents, so you got to make sure that you plug in those exponents. Okay, so we got some good information here, and we're going to look at the key characteristics of this equation. Right? And of course, you can plug in y equals here, and it's probably better if you do, but it's not necessary. As you can see, Desmos will read it either way. So we're looking for a few things. We're looking for the degree, the leading coefficient, the domain, and the range, and the zeros. Right? The degree and the leading coefficient we can find very easily. The degree is a 3, because that's the exponent on the highest exponent. The leading coefficient is 1, because that's the coefficient that goes with the highest degree. Okay, so what is a domain and a range? Okay, the domain is the set of all possible x values. The range is the set of all possible y values, or the set of all possible inputs and the set of all possible outputs. Well, let's look at the graph and see if we can determine that just from the graph. Okay. So what we can see here is the set of possible x values. Well, all we can see in this window here is going from, I don't know, around about -5 up to +5. But if we were to zoom out, well, we see that keeps going. I mean, we can zoom out as far. I mean, what if we zoomed out to infinity? Could we plug in, say, 1,000,000 for a value of x and still get something out of this? Well, yes, we could. We could plug in anything we want for the value of x, and we'll still get something, right? We'll still get a solution for y, whatever that solution might be. Okay, so our domain, therefore, is the set of all values, the set of all real numbers, right? So we can say that that's the set of all real numbers, or we can just say it's the range -infinity to infinity, and let's write it like this, so it's a bit more understandable for you guys right there. So that's your domain. It can go all the way from -infinity all the way to +infinity. And our range, similarly, we can see the same kind of idea going on there. Our set of possible outputs, well, it goes, you can see it's going all the way up to +infinity here. It's all going all the way down to -infinity down here. So our range is the same. Okay, this will make more sense when we start hitting situations where they're different. Okay, so finally, what are our zeros? What are our x-intercepts? Desmos can tell us this as well. And all we're looking at here is we're looking at these three x-intercepts at -3, -1, and 2. Those are x-intercepts. So we've got x-intercepts at -3, -1, and 2. So those are the x-intercepts we found from that graph. All right, so that's one there. We can see it's that one was pretty straightforward when we plugged it into Desmos. Let's look at another example. One more example. Okay, so we're going to grab this equation once again. We're going to change the fix the exponents on it when we plug it into Desmos. So go back and fix those exponents. Right. It's a much more interesting looking graph. There's a key thing I kind of want to, I know I've zoomed out a lot here, but a few things to notice from here. Let's deal with the ones that we can see just from looking at the equation first. Our degree is 4. Our leading coefficient is -1. Watch that negative right there. Okay, you've got a negative right there, so that's your leading coefficient. Okay, our domain, we can plug in any values for x and we'll still get a value for f of x. So our domain is going to be the set of all values from negative infinity all the way to positive infinity, right? And we can see that when we look at our graph as well. But when we look at our graph, we see that our range is different. We have a maximum point, right? We've no minimum point. It goes down to a negative infinity down here, but we have a maximum point. So our range is the set of all possible y values. Our highest y value is 262.894. So we need to note that, right? So our range is negative infinity all the way up to 262.894. I think that's what it was, right? So we've got a limit to our upper range, okay? That's also known as our maximum, right? And then we can start looking at our intercepts, our x-intercepts. We're not concerned about y-intercepts right now. Our x-intercepts are 1.085 and 6.867. We want our 0 in there as well. And 6.867 is our other one. Okay, so that's the information that you're going to be asked for from your equations. That's how to find it. And from there, you'll be able to go and do the worksheet if you haven't already done it. All right, any questions, please feel free to ask.